To the Cryosphere Pavilion. I am Gabrielle Kleber. I'm a postdoctoral researcher at the University of Tromsø in Norway, focusing on methane emissions from glacial and Arctic landscapes. Tonight's event is titled Multiple Threats to Polar Oceans. And I'll hand it off to Dr. Helen Finlay from the Plymouth Marine Laboratory in the UK, who will be moderating the event tonight.
Thank you, Gabby. Thank you to the International Cryosphere Climate Initiative Pavilion for allowing us to have the event here tonight. So our event is really looking at what's the latest science in the polar oceans. The other Arctic Ocean and Southern Ocean are critical components in the Earth system, and they bridge that gap between the oceans and the cryosphere. And so we feel that they're a component that needs to be taken account in our discussions about the cryosphere. So their unique ecosystems are under serious threat from warming, acidification, freshening, and ice loss. And they're already experiencing changes in chemistry. Continued warming is leading to range shifts and changes in food webs and ecosystems. And it gives me great honor to be able to have our first opening address with the Deputy Assistant Secretary for Oceans, Fishery and Polar Affairs in the Department of State's Bureau of Oceans and International Environment and Scientific Affairs from the US, Marlet Mesvin, apologies. So I would like to hand over to you to provide our opening address for this session. That would be great. Thank you very much.
Thank you, everyone, and thank you for inviting me to participate in this important discussion today. I'm delighted, and I understand I'm here to highlight a little bit about some of the U.S. government's efforts to address environmental change in both the Arctic and the Southern Oceans. And I'll start with some statements that are well known to this group, but I think they're still important because we keep them top of mind as we think about the work that we do. The Arctic is warming nearly 4 times faster than the rest of the planet. This dramatic warming has resulted in a marked decrease in sea ice extent over the past several decades, an increase in Arctic wildlife fires, and increasing permafrost. And climate change affects the people who live in the Arctic, especially Indigenous peoples who live in remote Arctic communities, as well as the resources upon which they rely. So in October of last year, the United States released our updated national strategy for the Arctic region, which summarizes some main lines of effort to address these issues. And I wanted to take today to walk through some of those. One of the pillars of this strategy aims to build resilience to the impacts of climate change, while also reducing emissions from the Arctic as part of our broader global mitigation efforts. We also want to improve scientific understanding of how climate change is affecting the Arctic and to conserve Arctic ecosystems. And so that's why these conversations are so critical and important. We will continue to partner with Indigenous communities in the Arctic, as well as public, private, academic, and non-governmental actors at home and abroad to harness the full range of knowledge and resources required to meet these goals. Another aspect of our strategy involves promoting international cooperation and governance. We will continue to work on implementing the agreement to prevent unregulated high seas fisheries in the Central Arctic Ocean, including through the joint program of scientific research and monitoring under that agreement, to understand the implications of climate change and safeguard a healthy marine ecosystem in the region. And finally, we'll work to sustain institutions for Arctic cooperation, including the Arctic Council, and position these institutions to manage the impacts of increasing activity in the region. At the other end of the planet, the United States also works to preserve Antarctica as an area of international cooperation for unique scientific research and peaceful purposes, while also assuring the protection and conservation of the living marine resources in the Southern Ocean. We do this through the Antarctic Treaty System, which includes the Antarctic Treaty, a unique example of international cooperation during the Cold War, as well as the treaty's environmental protocol and the Convention on the Conservation of Antarctic Living Marine Resources, otherwise known as CAMLR. Climate change is a threat to the biodiversity of Antarctica, particularly to ice-dependent species such as penguins and seals, facts that you likely know quite well. the Antarctic summer ice has decreased since 2016 and has been at its lowest for the past 2 summers. In November of last year, sea ice in the Bellinghausen Sea fragmented right under empire penguin rookeries, causing thousands of empire penguin chicks to perish, as they had not developed their feathers required for swimming. These empire penguins need sea ice to form breeding colonies, forage for food, and avoid predation. So according to the best available science, by 2050, their global population size will likely decrease by 26% to 47%. So to address this, United States advocated at this year's annual Antarctic Treaty Consultative Meeting to design the emperor penguin to designate the emperor penguin as an Antarctic specially protected species. And we are also working with partners around the globe to establish additional marine protected areas in the Ross Sea through CAMLR. The science clearly demonstrates that well-protected MPAs can provide substantial conservation benefits, including building resilience to effects of climate change. We know that there is a lot of work ahead of us to address the impacts of climate change in the Arctic and the Southern Oceans, and we are committed to working with allies, partners, and stakeholders from all sectors to sustain existing institutions of international cooperation. So I just wanted to thank you again for inviting me to join today and talk a little bit about some of the US thinking here, but I really look forward to the discussion and the continued engagement that we have as a government with science community and all our partners around the world around these issues that are existential. Thank you.
Thank you. And I think that sets the tone for really why we need to bring this latest science to the discussion, to be able to make sure that we are providing people like yourselves the latest information to get that information out and make action happen. And leading nicely on from that, we have our first speaker, which is Louis Papachiments. Hope I got that one right. I'm not very good with pronunciation, I'm afraid. I'm sorry. So Louis is here as the youth delegate for the Inuit Circumpolar Council. And I think you've got a range of different hats that you potentially wear. I was having a look on LinkedIn, personal assistant to the chair of the ICC, member of Overseas Countries Territories Youth Network, and also while being a master's student at the University of Greenland. So it's a real pleasure to have you here and provide that Indigenous communities Inuit perspective of the changes that you're experiencing and how that links to the latest science that we're talking about here and how we can potentially work together better to improve that discussion. So please, Roman.
Hello, Massi, Louis at Oppunga, Galatuna, Oppunga, Numi, the Hi everyone, my name is Louis Chemnitz. I'm from Greenland, born and raised in Nuuk. And as was mentioned, I'm a youth delegate at ICC. And this is only my second ever panel in my life. And the other one was earlier this morning. So ICC is the Inuit Circumpolar Council, representing all the Inuits across what is now 4 states, known as Denmark, USA, Canada, and Russia in Chukotka, representing about 180,000 Inuit across Inuit homelands, Inuit Nunangai. And you can see here the lands that we call the Inuit homeland, our homeland, Inuit Nunavut, marked in red. It was established, in 1977, before I was born. Just to give some context, I think we often talk about the Arctic without really knowing what we talk about, and it's often portrayed as a place where scientists goes, but there are also people living there, and I think that's very important to remember, and that these people have a unique sense of knowledge that is not only useful to us, but to the rest of the world, especially when trying to tackle the climate crisis that we are all together currently facing. So we live there, we hunt there, and we have thrived there for thousands of years. Just a little bit about our Inuit ecosystem. So Inuit really sees themselves as being part of the nature. We don't see ourselves as something that is outside the system. We see great connections between all the parts in nature. And it's also very closely linked to our understanding of conservation, which can sometimes vary from Western understanding of what conservation is. We really see that we are part of the nature, and we are able to sustain it by living with it. So Inuit knowledge is not only tied to animals or the nature, but is very it's the entirety of the natural world, and it has a very holistic approach. We often see with Western science that it goes into very specific things and zooms in on things where I think we can contribute with a greater understanding of things and the connection and zooming out and seeing things. So a picture we see is often that we use is this one, that every part is like a puzzle in the puzzle pieces, and they're all connected to each other. And if you try to remove one piece of the puzzle, then you don't get the full picture. So as I also said, that our understanding of conservation is through use. It also allows us to have an updated and in-hand understanding of our knowledge by using it. It's not only theoretical, but it's very practical. So we understand what we have learned through using that knowledge also. And yeah, it's not only about food security, but also protection. It also really touches on food sovereignty and sovereignty in general, that we are able to practice our culture and ways of living. And depending on the understanding of conservation, then Inuits and other indigenous people can sometimes sort of have a burden placed on them. Some work that ICC has initiated is this Bigelosorsuaq, which is a body of water between north of Greenland, Avanossuaq, and Nunavut, Canada, a province of Canada. And it's a body of water where the ice does not melt, does not freeze. The water does not freeze into ice because of the currents and wind conditions. And it produces a lot of the biodiversity. It allows for that in this area. So it's also an area where we do a lot of hunting. So in this area, we have worked to have free travel for Inuits across these lands, which has been the way of Inuit life also, that we did not have these, what we now have, state borders, which we also very much learned from climate crisis, that state borders do not exist when the whole world is affected by the climate change. And here are some pictures. We have hunters, of course, in Greenland, and there's an array of different kind of hunters, and some heavily rely on it. Some areas are really affected by the climate change, and others do it out of recreational use. And this is actually a partner of someone who works in ICC. We also took this photo of our Greenlandic sled dogs in the north of Greenland. So one thing I'd like to bring up is these protocols that the ICC has worked on for equitable and ethical engagement. And I shared some of these thoughts also on how these protocols really help to serve as a guide for those who wish to engage in the Arctic in the Inuit homeland. And there are 8 protocols. They're all available online, the document, so you can find that also. I highly recommend that one really understands the environment and the culture and the people and the knowledge system when engaging in our homelands. And then I just have a few words also. It was already mentioned that Arctic is warming 4 times quicker than the rest of the world, and we see a 2.2 degrees Celsius warming since pre-industrial time. So it accelerates faster in the Arctic. I'd like to share quotes that former Premier of Greenland, Ruby Kleist, and also President of ICC Greenland, shared, which you can find in the EEE protocol, where it says, "We know from experience that it is always beneficial to all involved to treat each other with the belief that we are all people and equal, and that we all want to contribute to a better world." And I think I'll stop there and leave room for questions later on.
Thank you, Louis. I think that's a great quote to move on to some of the science that will be presented here, and bearing in mind the ambition that we have within the cryosphere is to really raise that action, make sure that we're making change, and equity and goes along hand in hand with that. So good point to move on, I think. So our next speaker is Professor Michael Meredith from the British Antarctic Survey in Cambridge, UK. Mike is also a joint director of the UK National Climate Science Partnership, which is an initiative to harness and focus climate science capabilities of 8 UK institutions, and wears a number of hats as well, including as a fellow at the University of Cambridge, and has recently been awarded a number of medals, the Polar Medal, and is the president of the Challenger Society. So it's a very great pleasure. Where are you? There you are. To have you with us to talk a little bit about some of the polar oceanography science that's been going on, changes. Thank you.
Well, thank you very much. And it's a great pleasure to be here and contribute to this session. I thought I'd start by showing you this map, and it's a projection that I love very much because it's the ocean view of the world. This is kind of the fish's eye view of how the world looks. So instead of being the continents surrounded by ocean, which is the way that we humans tend to think of the world, this is the ocean surrounded by continents. And the reason I love this map so much is it does emphasize the point that there is only one ocean. And we often talk about the Atlantic Ocean or the Arctic Ocean or the Southern Ocean. In reality, there is only one ocean, and it is the biggest defining feature of our planet. There's also separate basins, but the ocean connects all of them, and it's the structure of the ocean that defines the planet as it is. The ocean provides connectivity across the planetary scales. The ocean circulation, it moves heat, it moves carbon, it moves nutrients, it moves all other substances around the world. And by doing that, it structures our climate, it structures our ecosystems, and it allows life to thrive on our planet in the way that it does. The arrows here are a cartoon of that ocean circulation. And there's 2 key points I want to draw out here. One is that the circulation around Antarctica is absolutely fundamental in connecting everywhere else in the world. but also where the arrows change color, that's the waters are transitioning. They're being reformed. They rise to the surface, they reform, they sink back down into the interior. And that's how the ocean can absorb the vast amount of heat and the vast amount of carbon that it does. That happens not just around Antarctica, you can see it also happens up in the Arctic. So these are the two most critical places in the world where the ocean is ventilated and our climate is structured. And the line at the bottom here makes that point. The vast majority of the global ocean was most recently ventilated at the poles. Without the polar oceans, our entire planet would be entirely different to how it is. So the ocean circulation is absolutely critical, and the poles are fundamental to that, but the poles are changing, and they're changing increasingly rapidly. The plot at the top here shows sea ice in both the Arctic and the Antarctic. The Arctic sea ice, we know, has been retreating and thinning very dramatically for decades. It's a cause of very great concern. The Antarctic sea ice seemed to be bucking the trend. It seemed to be hanging on, maybe even slightly increasing slightly. But then around about 2015, 2016, it finally got the memo about global warming. And since then, it's been a complete horror story. Antarctic sea ice has been retreating exceedingly rapidly. Linked to these in some ways are the ocean changes in both the Arctic and the Southern Ocean around Antarctica. Those changes include heating, they include freshening, they include acidification, they include loss of oxygen. There'll be plenty of evidence for all these coming up from the speakers that follow. The plot at the bottom is it's a very recent one, just to emphasize the point of how rapidly these oceans are changing and how extreme it is. This plot at the bottom shows the extremity of marine heat waves across the entire planet in 2023. The dark colors show the most extreme of these heat waves, and you can see that the Arctic is very badly impacted, as is the Southern Ocean around Antarctica. The Arctic, we knew, was always susceptible to these marine heat waves. We've always known for some time that it's vulnerable. The Southern Ocean around Antarctica was thought to be relatively immune to these. So this is a surprise in some ways, and a particularly unwelcome surprise, has to be said. What's causing the sea ice changes? The jury is still out. In Antarctica, we do know that the buildup of heat in the deep ocean is playing a role in these sea ice changes. The structure of the ocean in the Antarctic is such that a lot of the heat is stored at depth, not at the very surface. And that heat has built up over time. And then around about 2015, 2016, that heat was vented upwards somehow and got to the surface and started impacting the sea ice, impacting the sea surface temperatures in a very dramatic way. And it hasn't recovered since then. This year was the record low for sea ice extent around Antarctica. This has implications for regional ecosystems, it has implications for regional climate, it has implications for global climate. The parallel in the Arctic, again, is the input of heat to the Arctic. There's a process called Atlantification, and that's the increasing ingress of warmer waters from further south that are pushing repeatedly further north into the Arctic and bringing more heat, impacting the ocean, impacting the sea ice, and everything that depends upon it. So those are local changes that are happening in the Arctic and in the Southern Ocean. Very dramatic changes, very concerning changes. Coming back to the point I made at the beginning, the oceans all connect. These changes, there's every reason to think that they will have global footprints. And indeed, there are lots of lines of evidence that suggest that this is beginning to become manifest. This is one example. The plot on the right here shows the amount of deep water from Antarctica that is moving northwards up the Atlantic. So this is dense water that's produced on the shelves of Antarctica. It sinks to the abyss, it flows northwards, and then it becomes part of the overturning circulation in the Atlantic, which plays a big role in structuring European climate, North American climate, and so on. And you can see this amount of water is dwindling over time. On a decadal scale, it's going down. There are interruptions to that. It's not a monotonic change, but the long-term pattern is definitely downwards. This is one example. There are many others about changes in the waters that are being inputted to the global ocean circulation. So why do we care? Just emphasizing the point once more, all these things are connected. What this plot shows here is some of the connections on global scales between the Arctic, the Atlantic, the Southern Ocean, but then branching outward again to things like the Amazon rainforest and other elements of the planetary system. Some of these changes are what are called tipping points or potentially tipping points, where a change becomes self-sustaining. Others of these are not tipping points, they're just forced changes, but they are still very dramatic changes and they do have global consequences. And once you change the ocean circulation and the ocean heat uptake, the ocean carbon uptake, there are these vulnerable elements of the planetary system that can be altered and can be altered very dramatically. So the last slide, these are the messages I really hope you take away from this short talk. Ocean circulation connects across planetary scales and it's fundamental in structuring our climate. The polar oceans are absolutely critical to sustaining that ocean circulation. And we know that the polar oceans, the Arctic and the Southern Ocean, are changing very dramatically. These changes will continue into the future. We know that the poles are vulnerable to climate change more so than many other places on the planet. And so we can't turn off these changes much as we would like to. But what we can do is limit the amount of change that we're imposing on the Arctic and on the Southern Ocean. And by doing so, limit the risk of the other components of the Earth system that these depend on. So the final point, the vulnerability of the polar oceans to climate change is without doubt, but there are also global impacts of the polar change, and combined that makes it a really urgent driver for action to try and limit our impacts on the polar regions as much as we can. And I'll stop there. Thank you very much.
Thank you, Mike, and great to hear the sort of physical oceanography setting for a lot of these changes, and really emphasizing that these things don't just stay in the polar regions, they're actually important for all of us. So respecting the fact that communities live in the Arctic and their changes are being felt immediately, but actually these changes have implications globally to the rest of us as well. We need to work together to make that action happen. Which leads us nicely onto the ecosystem impacts in biogeochemistry. So we have Dr. Sian Henley here, marine scientist from the University of Edinburgh, and her research focuses on marine ecosystem processes in the Antarctic and Arctic oceans and how they are influenced by and also influence climate change. And Sian has been to a number of COPs now and involved in the UNFCCC process and is also serving as the co-chair on the Southern Ocean Observing System. So again, you have a wealth of experience and hats, and it's very pleasurable. It's our great pleasure to be able to hear you talk about ecosystems.
Thank you very much, Helen, for a very generous introduction, and it's a real pleasure to be with you here this evening. Similar to you, Louise, this is my second talk of today. So for those of you who were here earlier, you will recognise one slide that I presented earlier as well, but that's because it's the most important, so it's okay to keep presenting it. So Mike has set me up very nicely to talk about the ecosystems that inhabit the Southern Ocean and the Arctic Ocean. I am going to focus on the Southern Ocean, but some of the changes I'm going to talk about are equally as important or arguably more important in the Arctic, and I'll signal to when that is the case. So the changes that we've already heard are from Mike are focusing on the warming, the physical increase in temperature of both the ocean and the atmosphere, and the loss of ice and the effect that this has on the structure of the ocean. So I'm going to introduce a new climate change stressor to you in my short talk, which is equally important as these two and is more pronounced in the polar oceans than it is elsewhere. and that is ocean acidification, which is driven by the oceans taking up carbon dioxide from the atmosphere, and this causes a drop in the pH value of the oceans, which is an increase in acidity, which causes a stress on marine organisms. So this is a picture of a Southern Ocean food web in the marine ecosystem. And we can see in green and yellow at the top, center and left-hand side, those are the primary producers. So the phytoplankton and the algae, they produce carbon that everything else in the ecosystem is reliant on for its food source. So those primary producers are eaten by the copepods and the krill, and then it's those small organisms that are consumed by everything else that we recognize as an iconic Southern Ocean species. And what that means is that changes that are experienced at the bottom of the food web in those primary producers can have cascading impacts throughout the whole ecosystem because they influence the amount of food that's available for everything else. And as well as being important for its own intrinsic value and a significant contributor to global biodiversity, the Southern Ocean is also very important for the services that it provides to humankind, both close to the Southern Ocean and at great distances away. And these ecosystem services, as we call them, are also present, albeit in slightly different form, in the Arctic Ocean. So these are all relevant to both polar regions. So organisms take up carbon and store it for periods of time that are relevant to mitigating climate change. So they do us a real service in alleviating some of the worst effects of climate change. These regions are also hotspots for biodiversity, both regionally, but also by supporting global biodiversity, because organisms that live in these regions migrate in and out to lower latitudes on a seasonal basis. Now, the Southern Ocean in particular is a great exporter of nutrients, as Mike explained, and this actually fuels ocean productivity at great distances away from the Southern Ocean, all the way up to the tropical and equatorial waters, where the oceans are actually limited by the amount of nutrients, and therefore this supply of nutrients from the Southern Ocean is critical in underpinning ocean health and the fisheries that these regions support. And that brings me on to the final ecosystem service that we focus on, which is relevant for the Southern Ocean and the Arctic Ocean, which is the fisheries that are derived from these regions. And this is important for subsistence fisheries as well as economic fisheries. So we're talking about food security and economic value. So if we come back to our image and we add our stressors, we've got these three different stressors, but the important thing is that the sum of, or the total pressure by each of these stressors is much, much greater than the sum of its parts. So we have a combined impact of these different stressors, which place the organisms under much more stress than they would be if they were just affected by one or other of these stressors. So the ecosystem resilience is lowered, and therefore the impacts of each of these stressors is much greater. So to go into that in a little bit more detail, this image here shows the extent of ocean acidification. And as is often the case in these plots, red is bad. So in the top one, a value of close to or less than 1 signals that there is that the conditions are too acidic for organisms to be able to live comfortably and to do the processes that they need to do to survive. And then in the bottom plot, we see the exposure of a certain type of organism called a pteropod or a sea butterfly, which has a shell made out of calcium carbonate. So this is particularly susceptible to ocean acidification. And again, red is bad, with more or a greater proportion of these organisms being affected by ocean acidification. So what becomes very clear from this image is that ocean acidification is most severe in the Arctic Ocean and the Southern Ocean. So this is a problem that is much greater in the polar oceans than it is throughout the rest of the global ocean. And this has chronic impacts on organisms at all different stages in the food web. So the phytoplankton are affected by the cumulative stress of ocean acidification, as well as the loss of sea ice and increase in temperatures that Mike talked about. Antarctic krill, so specific to the Southern Ocean this time, is impacted in terms of its growth rates and its ability to reproduce, because it's reliant on sea ice over the winter. It requires cooler temperatures, and it's susceptible to the effects of ocean acidification. So the combination of all those stresses puts these organisms in a particularly vulnerable place, because they are susceptible to all three. Pteropods, we've just talked about. The sea butterflies have shells that corrode under acidic conditions, and they are also being pushed to the edge of the temperature limits that they can endure. And then marine mammals, for example, the crab-eater seal that's pictured here, but this goes for many marine mammals. They are under pressure from reducing sea ice, because they need the sea ice to haul out, to raise their young, to rest, and they are used to a cold, stable environment. So as the environment warms, that's an additional stress. And then their food sources, which are based on the phytoplankton, the Antarctic krill, and the pteropods, are also under stress and reducing in both the quantity and the quality of food available. So all of this adds up to incredibly damaging impacts on the species, the ecosystems that they're part of, and the benefits that they provide to human society. So if we look at the changes that we can expect going forward, we've got these plots that show the different climate change scenarios, the darker red being the business as usual high emissions scenario, all the way to light blue, which is the an equitable solution where we stick to 1.5 degrees of warming, and in this graph downwards is more ocean acidification. So we can see that under the higher emissions scenarios, ocean acidification is much worse, and it gets less severe the more action we take to reduce our emissions. But if we look at this regionally, we see again that the polar oceans are in danger of the worst effects under the high emissions scenario on the left. Now, on the right, we've got the low emissions scenario that is consistent with the Paris Agreement. And what we see is that the outlook is much better, but actually there is still ocean acidification occurring in the Arctic, even under the best case scenarios. And this has huge impacts on food security for people living within the Arctic, and also for fisheries that are in operation in the Arctic and subarctic and feeding people elsewhere as well. So this is an issue that is felt regionally, but also globally, because of the reliance on these fisheries for food security. So, and then when we consider that these effects of ocean acidification are also compounded by the increase in temperatures that we see at the higher emission scenarios, again with the dark red being higher emissions and the blue being lower. So the species that live in these regions are having to cope with increasing acidification and increasing temperature, as well as the sea ice losses that Mike talked about. And the combination of these three stressors puts these ecosystems in a perilous condition. And this can have cascading impacts throughout the entire food web, because species are so reliant on each other for a food source. So if the food source is affected, so are those organisms that rely on that food source. And for human beings, it is the impacts are most strongly felt in terms of the availability and nutritional value of fish and shellfish, both for subsistence fisheries and for economic fisheries. So I want to close with this image, and this is the slide that I also showed earlier. It's also my favorite photograph because I think it really captures the magnificence of the polar regions, but also their fragility. And I want to leave you with the message that to avoid serious and irreversible damage to polar ocean ecosystems and the services that they provide to all of us, we need deep and urgent emissions cuts to keep warming within 1.5 degrees. And I'll stop there. Thank you.
Thank you, Sian. And yeah, definitely the evidence for call for action there. I think we've got quite a lot of stories to tell in terms of how the ecosystems are being impacted. And the thing about acidification has always been interesting is that it's that direct link to CO2 emissions. We put more CO2 into the atmosphere, it causes acidification. If we put less in, then it's really able to show that we can do something about that. So moving on from these long-term changes that we're experiencing and we're expected to experience into the future, I'd now like to pass over to Martin Seigert, who's the Vice President and Deputy Vice Chancellor of the Cornwall campus for University of Exeter, a polar scientist who uses a variety of geophysical techniques to look at subglacial environments of the Antarctic, among other things. But Martin here is to tell us about the more shorter term extreme events and things, just to bring it back.
Thank you very much. Now, everybody. Very good. So yeah, I'm a glaciologist, and I've been working mostly on Antarctica, looking at the past and what's going on at the moment and in the future for over 30 years. And really, most of my work, the bulk of it, is continental scale ice sheet processes. That's kind of what I do. So this is a session about the ocean, right? So what have I got to contribute to that? Well, I found that through time, through those 30 years, in the 1990s, although looking back, it was kind of obvious that Antarctica was changing and climate was really going on, and there was this connection, but it's become more prominent ever since then. There's no doubt about that. And of course, all the action on where the ice sheets are changing is at the ice-ocean interface. So I, like many glaciologists, have found ourselves being attracted to the oceans. And I'm sure the same is true of the oceanographer has been attracted to the ice, but well, maybe not. So a bit of a background story to this paper that came out earlier in the year, Antarctic Extreme Events. So every now and again, I chair the UK Arctic and Antarctic Partnerships Committee, have done for several years. And every now and again, colleagues at the UK Foreign and Commonwealth Office asks that committee, the UK AAP, to do a piece of work, ask a question about something which we sort of thought was either not that interesting or kind of obvious in science. But, you know, sometimes when the policy world, where the sort of parliamentary world is asking a question of scientists, it's often a moment to take notice of what they're asking, because as scientists, I'm sure we like to think about what we're doing. Everyone must be interested in it, right? Including parliamentarians and diplomats and things, but often not the case. But when you get the reverse, it's probably a good idea to do a bit of work. So every now and again, we get asked these questions, and through the UK AAP, the Arctic Antarctic Partnerships Committee, we've got a huge source of information and collaborators. And Mike was part of this work, and there've been many others in it as well. So it came out earlier this year. And the genesis of this paper happened around about January this year, so early 2023, when I think I'm right in saying that there was an awful lot of snowfall in the Antarctic Peninsula, a very large amount. And the FCDO asked us the question, is this unusual? And what else might be unusual from the sort of extreme event perspective? So we sort of got a lot of people together and asked that question, you know, how has Antarctica been experiencing extreme events? Now, you'll know about extreme events from other parts of the world in terms of flooding, extreme heat and droughts and storms and winds, often attributed to burning of fossil fuels. So the wonderful work that Freddie Otto at Imperial College has been doing, formally linking a weather event with burning fossil fuels, because it just wouldn't be possible in our world without it. But we kind of asked the question in Antarctica, is it true there as well? So I don't have long, but let's go through some of the things. We can talk about a number of very high magnitude, low frequency, we think, extreme events that have happened. And I'm going to go through this, the paper charts a whole load of them, but I'm going to go through one or two with you now. And the one is in March of 2022, so a year and a half ago, there was a massive heat wave that happened in Antarctica, where an atmospheric river of warm air flowed essentially from Australia onto the East Antarctic continent. Now, it's really unusual for that to happen because the polar vortex prevents, and the orography of Antarctica, the shape of Antarctica, prevents really the longitudinal transfer of storms. It wraps around in a clockwise fashion around the continent rather than going straight across it. But this did happen in March, and it caused the temperatures in central East Antarctica to rise, to increase by, not 2, but by about 38 degrees centigrade. That is the warmest, the strongest heat wave that's ever been observed on our planet. I mean, crazy. The temperatures should have been minus 50 degrees centigrade. It was more like minus 12, right? And if it happened in the high summer, it could well happen. If it had happened in high summer, you could have experienced melting in central East Antarctica. That has never happened. I mean, not that it's never happened in our lifetimes. It's never happened even by the ice core record. It's just never happened. So that's just, I mean, highly unusual. Can we attribute this to the burning of fossil fuels? Not yet, and maybe not ever. And the reason for that is because we just don't have the meteorological observations to do the sort of the counterfactual on this that you would need to. There have been studies on heat waves. In 2020, the warmest temperature recorded on the Antarctic continent, 18.6 degrees centigrade, has been attributed to that, but lots of meteorological records there, but not here. So of course we suspect it is. I mean, it's just reasonable to suspect that that is the case, but formalizing it might be challenging. But take note, Antarctica is subject to extreme events. And then there's sea ice, and Mike talked about this. This might look quite complicated as a graph. You've got your months down on the y-axis, and you've got years on the x-axis. So each month between 1979 and 2023, we're working out the level, the cover of sea ice, and whether it's a record or not. So where you've got a blue square and a blue dot, that is the highest record growth in sea ice for that month has ever been recorded, right? And so you can see there's a transgression of blue dots from 1979 all the way down to sort of 2015, because as Mike was saying, if anything, the sea ice was kind of growing at that time. But also you can see there's a bunch of red squares with red dots in it, and that's the lowest sea ice on record for that month through time. And you can see there's also a lot of, so that not only is there been a reversal from that growth to, since about 2017, a decline in sea ice, all the way through this has been a lot of variability, a lot of records being broken on both sides. So, Signal is kind of doing this, going up and down an awful lot. And since 2017, it really has been going down. Now, I think it's too early to say yet, hand on heart, that this is because the Antarctic is starting to behave like the Arctic is. But of course, you would suspect that it is the case. And the next few years will be quite telling as to what happens. And it's really serious because, as Mike was saying, the Southern Ocean is, and as Sean was saying, the Southern Ocean is really fundamental to the habitability of our planet. And in particular, like we've observed in the Arctic, if you lose that white reflective surface and that sun's radiation doesn't get bounced back out into space because it hits the snow surface, but it gets absorbed because it hits this ocean surface or a land surface, losing terrestrial ice, then the planet warms up. more so. And of course, that's one of the reasons why the Arctic is warming up so much quicker now than the rest of the planet, 4 times than the rest of the planet. So this year has been crazy. And as we started learning about extreme events during the course of writing this paper, 2023 happened, like the warmest year on record, by some margin. I mean, we're 1.52 degrees warmer month on month in this year, pretty much since June. It's been an astonishing year, and the Antarctic has seen similar effects. This year's sea ice records, the lows, are just staggering. And what we've observed is a huge amount of sea ice that should have been growing in the winter that wasn't growing. And I was part of the UK Parliament's Environmental Audit Committee on Monday when I was asked not an unreasonable question, and I didn't have an answer to it at hand. What was the acreage of surface cover that has been lost? Right? It's a good question. We pretty much should have had an answer to that, but of course I've found it out. And it is staggering. Month on month, there's been something like 2.5 million square kilometers of ocean that should have been covered by sea ice that wasn't. Now, what does that mean to you? 2.5 million square kilometers. The UK's surface area is about 250,000 square kilometers. So it's like 10 times the area of the UK that should have been covered by ice. And it wasn't this year. And so the sun comes back and it's going to be absorbing heat. The air ocean's going to be doing it. So a crazy year. I don't really think this is El Nino. I mean, it takes a few months for El Nino really to get going. So what's going to happen in 2024? I mean, scientifically kind of interesting to work out. On a planetary perspective, really quite concerning. And then we have situations like this. This is 2014, and it's Nansen ice shelf. These are the huge slabs of ice that are floating, caused by flowing grounded ice moving into the ocean. And these things are fundamental to the stability of the ice in Antarctica. And we know that some ice shelves, Larsen A and Larsen B, and some others, have catastrophically broken up, like in a matter of days. And all the grounded ice upstream that was being supported by these ice shelves, acting as a force to keep them where they are, they will start flowing really quickly. So you don't have to melt ice to cause sea level rise, by the way. You just have to flow it from the land and into the ocean. Once it's displaced its weight in water, the job's done and the sea ice happens. And so one way to cause huge amounts of sea level rise is not necessarily just to melt the ice in Antarctica, but to break up the ice shelves and then experience accelerated flow of the grounded ice into the ocean. And so images like this, I mean, I've got to tell you, in the 1990s, if someone had said there'd be like a river of water in surface Antarctica in the ice shelves and there'll be a waterfall coming off the end, we would have said it just wouldn't happen. It's not. I mean, I've said it myself. It doesn't happen. And then this happened. If Captain Scott, 100 years ago, had been trying to get across part of the Ross Ice Shelf, which he had to walk over to get up the Beardmore Glacier, in 2014, he wouldn't have been able to do it. They'd have been stuck in sludge. But it's never happened. So another extreme event. Now, that alone doesn't cause the ice shelf to break up, but if it happens repeatedly and that water starts to refreeze, then the temperature of the ice pack starts to increase with the transfer of heat and energy. And then over time, it's possible for that water not to flow off the end of the ice shelf, but to flow down in holes in the ice shelf. And that will, in terms of the structural integrity of the ice shelf, that gets compromised. And that's what we've seen in Larsen A and Larsen B. So these small ice shelves are broken up. We're concerned about the bigger ones. And of course, we're concerned through further warming that this type of event that happened as a one-off, perhaps, actually becomes more regular. So 3 ways in which extreme events have happened in just the last few years in Antarctica. They're all different to each other, but they're all pointing to the same thing, that Antarctica does experience extreme events, and we should be really concerned about it, because this is the last decade or so of observation with further warming, right, we're going to see the strong likelihood we're going to see more and more of these sort of things with all sorts of impacts to the oceans, to our atmosphere, and to global sea levels as well. Thank you.
That's really, really good. And I think just highlights that we talk about these long-term changes and they're really important, but actually understanding that variability and extreme events is really fundamental. And actually coming back to the sort of ecosystem impacts, it's actually a lot of that extreme events that the ecosystem responds to. They respond to these long-term changes, but actually they're very much involved in the dynamics of these extreme events. In the interest of time, I think we'll move over to some questions. So I'd like to say just thank you very much to everyone. I think it was really great to get those different perspectives. So I'd open up the floor if there are any questions just to our speakers to hear about anything more that they've said. You want to kick us off? Yeah, sure.
My name is Tracy. I'm from New Zealand. And heard a bit about acidification and warming of the oceans over the years. As I was listening to you speak, Michael, I had a new sort of doomsday vision that I hadn't think before. But I think maybe you can inform it. Then you mentioned that the deep heated water is reducing. And so I was thinking about the convection currents and if the contrast between the warm and water's changes, is it going to slow the convection so it can convey about with the oceans? Is there much research looking at the speed of current of the oceans as a symptom and what does that look like? And, is the ocean just going to slow down and stop moving? Or, yeah.
Great question. There's a lot of interest in that. One of the issues is that ocean circulation is actually really quite hard to measure in a very large scale sense. You need an awful lot of sensors distributed over a very big area. So what the community has done is kind of focused its observing efforts on a few key places that it thinks are really important. So for example, there's a gateway from the Arctic where there's a lot of ocean observing, and there's a line of sensors across the North Atlantic called the Rapid Array. Where there's an awful lot of oceanographic sensors measuring the ocean circulation there. There's some around Antarctica as well. One of the issues is the Southern Ocean is so huge that you can't monitor everything as well as you want. What we are seeing seems to be that, the production of dense water, for example, in the Weddell Sea in Antarctica, is decreasing over time, and its export from Antarctica is slowing. There are changes in the Arctic that seem to be influencing the Atlantic system of overturning currents. And that makes a lot of sense. There's a lot of theories about how the ocean currents will respond as you put more fresh water into the ocean. So if you melt Greenland around the edges, or melt a lot of Antarctica around the edges, you make it harder for that water to sink. That's the deconvection. If you make it harder for that water to sink, then you can put less of that water into the ocean. So I guess the headline result is in the Atlantic. The currents over the time, so we've got direct measurements, it's a little bit unclear, but there's been reports of it slowing. Then if you connect that with the kind of paleo indicators on ocean circulation, there's good evidence it seems to be slowing down over time. And that means that heat transport in the oceans will slow, nutrient transport and so on. It's not going to be the case that ocean circulation will stop entirely. But even a significant slowing of it could have a major impact, climatically. So it's a really important subject. We need to know far more about it. The indicators that we do have are concerning, and things like the Atlantic overturning circulation probably slowing down over time.
Thank you. Anyone now? Yeah.
How is the observation systems of the Antarctica? So is it easier to observe the Arctic than the Antarctic? into us.
Do you want to have a go at that?
Yes, I come here for the live stream. Yeah, so with my hat on as co-chair of the Southern Ocean Observing System, maybe I'm a good person to answer this. So as observational scientists, we want to measure everything, everywhere, all of the time, but that's not possible. So we have to target our efforts on the areas that we think are important and the times of year that we think are important. But in both polar regions, there is a great difficulty in observing during the winter, the early spring, and the autumn. So there's actually quite a lot of data for the summer for both polar regions, but it's those other seasons where there is a lot less. I think in the Arctic, there are more observing efforts from different groups and different organizations, but they're less well coordinated. Whereas in the Southern Ocean, there are fewer actual measurement stations, but internationally, they're better coordinated. And that's because research in the Antarctic is kind of within the framework of the Antarctic Treaty System, which is by its very nature a very international collaborative thing. Whereas because the Arctic has nations that call it home and people that call it home and great efforts that have been going on for much longer, it can be more challenging to bring those things together. And I think in what the Arctic has hugely that the Southern Ocean doesn't have is local and traditional knowledge, which is a different type of knowledge, a different type of knowledge system to westernized or southern scientific knowledge. And I think historically scientists have been really bad at incorporating traditional knowledge. I think it's something that we're getting better at, but there's still plenty of improvements to be made. So I think in both polar regions, there's plenty of work to do, but good progress is going to come from people working more effectively together and making good advantage of the data that are available, rather than necessarily just generating endless more data.
Louis, do you want to come in and comment on the Indigenous knowledge side of things, or you're welcome to come up with me? Don't feel you have to, but just an opportunity.
Yeah. I'm not sure.
It's no worries. Any further questions? Yes, please.
For you. So I've been working with colleagues that work in the active process, and they've been collaborating a lot with the local community people, and especially with the fishers. The focus really surprised me as a system modeler. Because it's here that what we often say that we are observing new species around the Arctic. But what I understood is that what we call new species for you are more like rare species. So it seems that our knowledge, for as much as we are trying to get there, is pretty much limited to, and what we think of something new and that has been rare also before. So it's more like, is it so?
That's not a question I can answer directly. I think one of the strengths of indigenous knowledge is that we do have a very good sense of generational knowledge that is being passed on again and again. And I feel that can serve as a strength in having knowledge about what has happened before, and therefore being able to say that this is these are rare species instead of new species. I think that's sort of the background, so it's why it's possible to say that. But personally, I'm not able to.
It's very important information for us because it makes also assessment how the ecosystem is pretty much different if something is new or if something has been there before. So we're very fascinated.
We've seen how sometimes there are contradictory sayings from biologists and from hunters and fishers in Greenland, where the hunters and fishers have a very broad sense of understanding. You have examples where scientists conducted research in a very specific area, and that the conclusion was in contrary to what the hunters were saying. And if that research had been conducted in a different place, it would then have been in line with what the hunters were saying, because they had a better understanding of how things were changing in the environment and so on. So, yeah.
That's why it's very important we collaborate.
I think.
Absolutely. Any further questions from the audience? In that case, I think we'll wrap up. It was a really delight to have you all present. So if you could just give the speakers another round of applause. And yeah, just to end on saying that I think we have a lot of evidence to really go for action now. So over to the negotiators and the team that are working hard behind the scenes of COPs. So really getting that message out to them that we need to be putting action in place. So thank you very much. Thanks.
Thank you.